All right, we're going to continue our discussion of the muscular system. Remember in the last video that you watched online, talked about how muscles use energy, and there was a really good slide that kind of summarized in order how we use energy. So I want to quick just draw your attention to that. We don't spend a lot of energy storing ATP. We like to just have it available for a brief period of time, and then we can go and make more. So stored ATP is really in a short duration fuel because we could go make more. But a quicker way than waiting for those aerobic pathways to kick in, remember, is the special molecule we find in muscle, which is creatine phosphate. So that provides the phosphate to convert ADP to ATP and get those myosin heads and actin interacting. So we've got stored ATP, 6 seconds, that's gone. Creatine phosphate, we get another 10 seconds, then that's gone. And then glycogen that's stored in our muscles. So if you've been training for an event, you can go and grab glycogen stores. So that's going to depend on the individual, how well trained they are, how many glycogen stores are in their working muscles. And then we wait for those aerobic pathways to kick in, Krebs cycle, electron transport chain, and then we can keep going and going and going. And with training, again, we have more glycogen stores, we have more blood vessels to working muscles with training, and that all depends on the individual, how efficient that is. But we're always going to feel the burn of lactic acid in the first few minutes of exercise because we're always using those anaerobic pathways to get started, because it takes a while for the Krebs and the electron transport chain to get going. And a classic example of that was this weekend when I was running a race down in Florida with my son. It was just a 5-mile race. They said it was 4.8. I was quite upset. What?
Just 5 miles?
Yeah, well, yeah, depends where you are on the training spectrum, yeah. But so he never runs, my son doesn't. He's 13, but he plays a lot of basketball, so he's in good shape. So we're starting off, and he was going to run with me. Well, he realized very quickly he did not want to be with a slow mom, so he took off, and he ran like a 7-minute mile, and with no training, just, you know, finished the 5-mile, and he was miserable afterward. His gut was, he was on the toilet for a long time, because when you're not trained and you don't have good blood supply to your muscles and glycogen stores, the body has to divert blood from the digestive tract during your run, and then, you know, the muscles can perform during the run, but after that, the bowel is in a state of shock from not getting that blood supply during the run, and then people end up on the toilet with cramping and diarrhea because they weren't in shape. So it's important that when we're engaging in intense, longer exercise that we're trained. And you often see that in like middle schools and high schools in the beginning of the season. You know, the coach comes up and figures everybody's young and in shape and says, okay, go run 3 miles and we'll see you back here. Well, for kids that have sat around all summer, they're not in shape for that, and their connective tissues are not in shape either. Like my son, he's like, can we sit down? Can we sit down? I'm like, what are you talking about? You know, we only ran 5 miles. And and he's like, my calf muscles and my Achilles tendons are killing me. Well, again, he was straining those connective tissues that are not used to that. And there are middle-aged men that get into running, and they're maybe 30, 40 pounds overweight, and they get on, you know, these little training regimens of running, and they strain their Achilles tendons, where men have actually ripped the Achilles tendon off the back of the heel because those tissues are not trained and tough from gentle training. And it's a big problem that we see in the middle age is people that are athletic, like myself. I have to really be careful when I start running to do it gradually and not strain those connective tissues, because then you have torn ligaments, torn tendons, and muscle injuries, and you see it all the time. And that's why when I run, it sounds like 5 miles, ooh, impressive, but I do a walk run. I don't make myself miserable. When I'm feeling miserable, then I walk for a little while, and then I run for a little while, then I walk for a little while, because you really got to take care of your connective tissues as you get older. They get less resilient, and you're more prone to injury. So, but I wanted to talk about this, and when we're in an oxygen deficit, how do we know we're in an oxygen deficit? Do you remember from the previous video? Heavy breathing, yeah, you're repaying your oxygen debt when you get to the top of that. And that's just the way the body can convert that lactic acid back to what it needs. So depends, where we are. If we're still, working hard, then we're not going to go all the way to glycogen. But if you're sitting down in class, then you're going to convert that back to glycogen. So, all right. And again, most of the energy that we use that we break down from glucose is not actually converted to muscle contraction. It's given off as waste heat. So 60% is given off as heat. And we know that the more we're moving and exercising, the more heat we give off, right? And that's still efficient. 40% conversion of glucose to energy is still an efficient machine. Okay, so now we're going to talk about smooth muscle and how that's different than skeletal muscle. And those of you that have had children know the power of smooth muscle, right? Or maybe you've heard stories of people that have delivered their babies in the car, close to the hospital, because that smooth muscle, when it's contracting and baby's being born, for some people, there's no stopping it, and that baby comes. There's people that years ago, they used to give gas, like a laughing gas, like a twilight gas to the woman. The minute the woman was fully dilated, she left the labor and delivery, or the labor suite, and went to the delivery suite, and they deliver that baby without her even being conscious, which is not good for delivery, because we know that if the mother helps with pushing, there's less injury, there's less use of forceps and the vacuum little suction cup that we sometimes use to pull babies out. There's less need for those, and less need for C-section if the mother is helping. So smooth muscle is not to be underestimated in its strength, because it can really be powerful, but it's more gradual than skeletal muscle, and the way it's laid out to do what it does is different than skeletal muscle, and we're going to talk about some of those. So where do we find smooth muscle? In the walls of our hollow organs and in our blood vessels. So we have smooth muscle in our blood vessels and the walls of your hollow organs. So what are some examples? I wish I could type rather than, can I type with this? No. But where do we find it then? In the bladder, right? In the uterus, the urethra, I'll just use the first couple letters. In the GI tract, right? We said our blood vessels have smooth muscle. And we remember those blood vessels always have sympathetic tone, so they have some amount of contraction to maintain our blood pressure. If we got rid of sympathetic tone, blood vessels would relax and blood pressure would drop, and we wouldn't get blood flow to our brain or vital organs, and we would die. So very important that we have a little bit of sympathetic stimulation to keep that smooth muscle in those blood vessels contracting. So we find it, in the heart, we don't have smooth muscle, we have cardiac muscle, which is kind of a medium, kind of in the middle, I should say, between skeletal muscle and smooth muscle with some of its features. And we'll really study cardiac muscle when we get into the cardiovascular system next. So when we look at how smooth muscle is laid out in the cells, the cells are very small and spindle-shaped, and those cells are laid in sheets in two different layers. So we have the longitudinal layer that runs lengthwise. So the longitudinal layer runs down the length this way. Oh, it won't let me draw on pictures. But the longitudinal layer runs, what the heck? Runs this way. That's the longitudinal. And then the circular layer wraps around the organ and runs this way. So when the longitudinal layer constricts, what is that going to do to a hollow organ? If it runs left and right and it constricts, what is it going to do to that hollow organ? It's going to shorten it, yep. So the longitudinal layer shortens when it constricts, shortens the organ. And what does the circular layer do then? If it wraps around it like a belt. What's the clinical term for squishes? Narrows, even more clinical than that. Starts with a C. Constricts, yeah. So the circular layer constricts the organ. So these sheets of cells, small spindle-shaped cells, really help move things through, because when we shorten and constrict, that pushes things through our GI tract. And we always have some amount of parasympathetic tone to our hollow organs because we're always moving things through. We're always digesting when we're sitting in class, and we're always making urine and moving urine from the kidney to the bladder through those ureters. So they're in two different layers, and we have respect for this smooth muscle shortening and constricting. If you've ever had an asthma attack, you know how that feels, right? That's because of some allergen, something that's creating histamine and causing that asthma sensation, or that, you know, that the airway constriction sensation that occurs with asthma. And also stomach cramps. If you've had abnormal cramping because of something you've eaten, or maybe it's stomach bug, stomach virus that is causing smooth muscle. And then menstrual cramps too is cramping of the uterine wall. That too is painful. So, you know, again, it's a powerful contraction. So peristalsis is the term we use for these wave-like contractions of both layers, the longitudinal layer and the circular layer. And it can be painful. And we know that uterine contractions during childbirth, they kind of rise. They start out slow, you know it's coming, and then it rises and peaks, and they put a little belt around women's uterus, around their abdomen, and they can measure the strength of those contractions. They also measure the heart rate of the baby during those contractions to make sure the baby's tolerating the contractions, because sometimes they don't. If heart rate slows with contractions, they start to get a little concerned, because what often that can be a sign of is the umbilical cord is around the neck. So when you squeeze, you know, around a baby with the umbilical cord around the neck, that can be dangerous. And that happened with my last child. And pretty soon, you know, I could hear it. You can hear because they have two belts, one for baby's heart rate, one for measuring the contraction. And I could tell when the contractions were going, all of a sudden the sound of that heart rate was going from sound to. And then now there's more nurses in the room, and they're all staring at the monitor. And pretty soon I'm looking at the monitor. And then my husband would stick his head in between my face and the monitor's like, just focus on pushing. Get out of the way. Easy for him to say, right? But yeah, so when she was born then, she had the umbilical cord wrapped twice around her neck. So it's really scary. And when that baby's tumbling around in there, there's umbilical cord accidents that have been fatal for developing fetuses. So it's kind of a scary time, and they're always wanting you to make sure there's movement every day. And for me, because I was a little overly analytical, I bought a little Doppler. You can rent them online, and you can have a Doppler, and you can check baby's heart rate anytime during the day, which I really liked. It was like $20 a month or something, and I just had it for the last half of pregnancy when you can hear the heart rate. Anyway, so looking at how smooth muscle is different physically then, like I said, they're short, spindle-shaped fibers, and they don't have as much connective tissue attaching them. Like we need more connective tissue, like where there's epimysium, which is that top layer of connective tissue that we see in skeletal muscle that forms tendons and connects it to bone, tendons and ligaments. So we don't see that in smooth muscle. It's not necessary. The sarcoplasmic reticulum, do you remember the role of that in skeletal muscle? It's a special smooth ER that's modified in skeletal muscle. Do you remember what the function of that is? Yeah, it stores calcium. So the SR is less developed in smooth muscle because it's not as important as it is in skeletal muscle. Most of the calcium for smooth muscle contraction comes from the extracellular fluid. So there is still some release of calcium from the SR, but it's not as vital to contraction as extracellular calcium. So there's also these little infoldings of the plasma membrane of smooth muscle cells that help store calcium, and they're full of voltage-gated calcium channels. So they not only act like little reservoirs for calcium that's floating around in the extracellular space, but it actually stores some, or actually promotes the movement of calcium by having lots of voltage-gated calcium channels. So when you see caveoli, Ca, just think calcium. So again, voltage-gated calcium channels. We find lots of them lining this little in-pouching of the sarcolemma. So caveoli calcium. That's not something we see in skeletal muscle. So that's unique to smooth muscle. Another thing that we don't see in smooth muscle are there are no sarcomeres. There's no regular repeating pattern of myosin and actin with the Z discs. Remember, a sarcomere was Z disc to Z disc. There are no Z discs in smooth muscle. There's another structure called dense bodies. Oops. I was talking and writing at the same time. Z disc. You can read that. No Z discs. So they doesn't have a regular pattern, and that's why we say they're not striated. They don't have, they're smooth. Remember, striations are that kind of that striped appearance that skeletal muscle had, if you remember that from general A&P when you looked in the microscope and had those vertical lines, right? We don't see that in smooth muscle. That's why we call it smooth. There are no Z discs, no real organization in terms of, you know, parallel arrangements of actin and myosin. So this just is a nice little chart that describes what we're talking about here, differences between smooth, cardiac, and skeletal. I'm not going to hold you accountable for skeletal or cardiac because we're not talking about cardiac yet. We're just comparing and contrasting skeletal to smooth. So don't worry about this column yet. We will get into that in the cardiac muscle unit. So how smooth muscle is stimulated to contract is different than skeletal muscle. Remember, the autonomic nervous system is what controls smooth muscle, right? Autonomic nervous system, we said, is smooth muscle, cardiac muscle, and glands. So we're in the smooth muscle category. So the parasympathetic and sympathetic nerve fibers stimulates or inhibit smooth muscle, right? What stimulates the GI tract? Parasympathetic or sympathetic? Parasympathetic. So those neurons, that's what's shown on the bottom here, those autonomic nerve fibers. If this is a sheet of smooth muscle in the GI tract, that's going to stimulate contraction, the parasympathetic neurons. And what neurotransmitter stimulates the GI tract to contract? Is it epinephrine or acetylcholine? Acetylcholine. The GI tract is also stimulated by different hormones as well, and we'll talk about that in the next unit when we get into the digestive system. So autonomic nerve fibers are what stimulate smooth muscle, not somatic, right? Because somatic is skeletal muscle. The term somatic refers to voluntary skeletal muscle. So we're talking about autonomic because we're referring to smooth muscle. And there's something called diffuse junctions. What did we have in skeletal muscle? No, what do we call that little, where the axon terminal and the skeletal muscle, sarcolemma, come together? There was a special name for that junction. It was called the Neuromuscular Junction. Remember the Neuromuscular Junction? And the motor end plate was where one axon terminal came close to, but not in direct contact, but one axon terminal was real close to the muscle cell membrane, and then it released its neurotransmitters to that little spot, right? So the neuromuscular junction is part of skeletal muscle. We have diffuse junctions. And what diffuse means is these are wide. They're wide and not very specific. Diffuse means kind of like spread out. So these varicosities are swellings. It's not one branch of a motor neuron. These are autonomic neurons, parasympathetic neurons, if we're talking about stimulating the smooth muscle. And they have multiple swellings on the end of those neurons that release neurotransmitter kind of like a sprinkling over a wide area. Kind of like crop dusting, right? Like a plane coming down and crop dusting, or bulk mailings that just kind of go to a whole neighborhood. It's not very specific, like a bill, right, that would go to one individual home. That would be like a skeletal muscle. When you have one axon terminal, right, stimulating a muscle cell, that is more specific. These are more diffuse. So when we look at the contraction response, it's slower and more widespread because those neurotransmitters released by the varicosities are spreading over a wider area. So there's kind of like a group contraction. More than one muscle cell is going to contract. And there's other connecting things that make it contract as a sheet, and we'll talk about that. So we have these varicosities, which are on the end of the nerve fibers that release neurotransmitter over a diffuse junction. So I'm going to just pick up another color here. So diffuse junction, varicosities, and autonomic nerve fibers. Those are all unique to smooth muscle that we don't see in skeletal muscle. Okay, if we look at the ratio of actin and myosin, there's a ratio of 1 to 13, so there's a lot more thin filaments than thick filaments. So a lot more, let's just refresh our memory. Thick filaments, remember, are myosin. And thin filaments are actin. So there's a lot more actin compared to myosin in smooth muscle compared to skeletal muscle. And the thick filaments have heads along the entire length, which means that they can maintain a strong contraction compared to skeletal muscle. Because skeletal muscle, it starts to move that actin filament to the center, and then it needs more ATP to move it again. And then when there's no more myosin head to line up with actin, contraction stops. But we have a stronger, more longer duration contraction with smooth muscle. So we get a longer contraction. And again, if you've had a child, you know what that long contraction feels like during childbirth. That was another funny story I remember. So my parents came in during one of the labors of my kids, and my dad was watching the thing, and I was getting to the uncomfortable stage where those contractions are really hurting now. And my dad's like, oh, here goes 1, 2, 3, and he's counting up as it's getting more painful. And I was just like, please don't, because I'd rather just imagine that it's going to be going away rather than continuing to climb, right? So don't ever do that if you're in with somebody. Don't count their contractions as they rise. All right. Yeah, right. Yeah. You don't need to be reminded, right? So there's no troponin in smooth muscle, but there's a special protein called calmodulin that binds calcium. So again, a little hint, cal in calcium. So calcium binds calmodulin in smooth muscle cells. And those myofilaments, instead of being overlapping and making those striations, they're spirally arranged around the muscle cell. So when the muscle cell contracts, it twists. And again, they're attached to each other, these muscle cells. So the whole, we talked about the circular layer, the longitudinal layer, when they both are contracting together, they're shortening, constricting, and twisting. So that really helps propel things through those hollow organs. And then we have dense bodies, which are similar to Z discs. And that's what tethers the filaments together. So all the muscle cells pull on each other. So they're like Z disc, the dense bodies are. So you can kind of see that on here. And yet another structure are gap junctions. What do we know about gap junctions? We talked about those before. I thought I could highlight on my... What are gap junctions for? Not the neurotransmitter. Neurotransmitters bind to the surface and open up ligand-gated channels. But what's flowing through those channels? Ions, yeah. So ions flow into the cell, and then they can flow to the next cell nearby through these gap junctions. So think of gap junctions as just doors between cells. So they're just doorways between cells for sodium to flow from one cell to the other. That causes the nearby cell to depolarize, and then potassium flows through, and we have this flow of ions. So these are doors between cells. I'm not going to write all that. You can add it. But they're doors, and again, ions are flowing between cells. So we can spread an action potential very quickly when we have gap junctions. And where did we see gap junctions? Do you remember where I talked about those in the neural unit? Say it louder. I heard the word. Who said it? Who said it? What is it? Where do we find gap junctions? What? No, no. Who said that? Is that you, Katie? Okay, yes, electrical synapses. Yeah, because chemical synapses, there's a space between the two neurons. You've got the axon terminals and the dendrites, and there's a space. But in electrical synapses, they're connected. So you have the dendrites and the axon terminals that are connected, and there's gap junctions between them. So ions can flow. We don't have to rely on the release of neurotransmitters. Ions flow directly from one cell to the other. And that's how we spread an impulse. Okay, so we talked about the dense bodies, the gap junctions, the caveoli. Now, something happened to this slide. I don't know what was supposed to be there, but so calcium. So in skeletal muscle, calcium binds to troponin, pulls tropomyosin out of the way, myosin binds to actin, and we have contraction. Well, it's a little different in smooth muscle. Some calcium is released from the SR, but a majority of the calcium comes in from the outside of the cell, from the extracellular fluid. So most calcium is coming from outside the cell. It's from the extracellular fluid. And how do they get there? What special structure did we say smooth muscle cells have that have lots of voltage-gated channels to sequester or to grab extracellular calcium? What do we call those infoldings of the sarcolemma? That caveoli. Yeah, think of ravioli, caveoli, okay? And that grabs that extracellular calcium. So do we need calcium in our diet for good muscle contraction in our gut? Yeah, for sure. So we know we need it for bone health. We need it for muscle and nerve interaction because it lets acetylcholine, remember when it voltage-gated calcium channel enters the axon terminal, it allows neurotransmitter release. So we need it for that. We also need it for smooth muscle contraction. So lots of roles for calcium in our body. So if you're not getting good calcium, there's lots of effects of that. We're going to talk more about how it affects the heart as well. Okay, so what happens then? Calcium enters the cell. This is kind of a small diagram. I'll make it bigger here. So here's this caveoli, this little indentation that has voltage-gated calcium channels. So that comes into the cell. And then that triggers there's some release from the sarcoplasmic reticulum. And then that calcium binds this special protein called calmodulin. And when it binds calmodulin, that binding of calcium to calmodulin activates an enzyme in smooth muscle cells called myosin light chain kinase, or MLCK. So those enzymes then act as another enzyme converting moving a phosphate from ATP to ADP on the myosin head, which energizes it. So when ATP splits on the myosin head, that's how it is activated, cocked, to connect to actin and then cause contraction. So it's once we get the process started, then contraction begins. But it requires this calcium binding to calmodulin, which activates myosin light chain kinase, which assists in the phosphorylation of the myosin head to give it its energy. So what you need to know is just the differences, those first 4 steps that are different than skeletal muscle contraction. Okay, so if we look at the contraction of smooth muscle then, it responds to stretch. Unlike a skeletal muscle, when I stretch a skeletal muscle, it goes back to its resting length. So you stretch it out and it's back to its resting length. Smooth muscle can develop new resting lengths, which, with the case of a developing fetus, you don't feel the stretch as that baby is growing and growing, not only because of that, but also because of hyperplasia. This is something we know is not the case in skeletal muscles. They can divide and increase their numbers. We call that hyperplasia. So the uterus starts out, if you're a non-pregnant female right now, your uterus is about the size of an orange or a peach. It's pretty small, but it feels pretty miserable during menstrual cramps if you get those. So again, can't underestimate that. But think of the size of it when a woman is ready to give birth. Or I know 3 different people that are having twins this spring. 2 are identical. 2 of the pregnancies are identical and 1's not identical. But anyway, think of the size of that uterus by the time those babies are ready to be born. It has increased in size. We call that, again, hyperplasia. The same thing can happen when we overeat. We stretch our stomach, and then it has a new resting length. And I've talked about that before. So then we feel, as it starts to get smaller, we feel those urges to eat because our stomach is stretched. So we talk about, we did the diet reports in class, but really the best way for nutrition and feeding metabolism, you've always probably heard, is 6 to 8 small meals a day, right? Keep the furnace burning, don't let it go empty, and then overstuff it, because we get an overly stretched stomach, and then your brain is looking for more food when that stomach starts to shrink beyond that resting length. And that's how people that are morbidly obese get morbidly obese, because they overfill their stomach, and that stomach stretches and stretches and stretches and can hold more food. So when they go out to eat, they can eat a large pizza and a 2-liter bottle of soda just themselves. And again, mix that with no movement, and you've got a recipe for extreme obesity, right? So it's really important, if a person is trying to lose weight, not to starve themselves and then get home and eat a bunch of food, because now they're stretching their stomach and they're going to feel those hunger pains more. And I've noticed that myself. Like if I spend a weekend camping, like, in the summertime, camping is all about eating and drinking and eating and drinking. You finish breakfast and you say, what's for lunch? And you start planning lunch, right? That's how we are. Or the holidays, right? It's all about eating and drinking. And then you go back to work or school on that Monday after a weekend of just celebrating, and you're hungry, right? Your lunch that satisfied you on Friday at work is now not nearly enough on Monday, because you've stretched your stomach out over the weekend. And it takes a couple of days to get back to normal again. So it's really important that, with our patients too, we not let them go for long periods of time without eating, because again, that's going to shrink their stomach, especially if they just had surgery. And some of these people need to eat protein and get stronger, right? Like little old ladies that have had hip surgery. We don't want their stomach shrinking any smaller than it already is. We need to make sure they're eating a little something. Otherwise, they're going to lose weight and decondition. Okay, so that stress relaxation response, so it gets a little stretched, right? And then it relaxes. And that's good, because when you feel that stretch that you have to use the bathroom, when you have to urinate, your body can sense that stretch, and then that reflex is suppressed by our brain, and we don't feel the little twinge that we have to go to the bathroom, right? But then it comes back, and then you feel that twinge. And as it stretches more and more, pretty soon the twinge happens constantly, and that's when you stop and you say, that's it, I have to go to the bathroom, right? Like if you're working on a project on the computer or working at work, it's like you get to that point, I gotta go. So it's a good thing that it doesn't cause us to instantly run to the bathroom, the stress relaxation response, but it could be a bad thing if we don't respond to it, like kids, right? Kids feel the twinge and they keep on playing, or they continue whatever they're doing, and next thing you know, they wet their pants. So the good part, like I said, is that we can store our urine, and food until it's time to go. So another really important function of smooth muscle is it can contract when it's not full, right? We know, like I tell my kids all the time, like when we're traveling, okay, we're going to go to the bathroom. No, I don't have to go. Well, I don't care. You're going to go anyway, and you're going to empty, so we're all on the same schedule, right? That drives me nuts. And as some parents don't have their kids do that, like we'll have play dates over, and the kids are like, I don't have to go. Well, I want you to go anyway. Well, I don't need to. Right. I don't need to. And they just say no. And that's like, because then, of course, you're stopping when it's not convenient, right? So anyway, so it can still contract even though it's not full. All right. So again, hyperplasia, know what that term means. The uterus can get bigger during pregnancy. And then our last topic is single unit versus multi-unit smooth muscle. So you need to know where these different types of smooth muscle are. So multi-unit smooth muscle is more like how skeletal muscle works. It needs a stimulus, and that stimulus is usually a hormone, a neurotransmitter to bind, or a neuron directly stimulating it. So we find these in the airways leading to our lungs, large arteries, the erector pili muscles, the iris of the eye. So they need some stimulus from the nervous system. And we get graded contractions, so varying strengths. So we call that multi-unit smooth muscle. Now, when we say multi-unit, it just means that there's more than one smooth muscle cell that has to work together to get varying strengths of contraction. Now, single unit smooth muscle contracts as a unit. So when you say single unit, all you need is an action potential, because those gap junctions are going to spread that action potential to nearby cells, and it's going to contract as a unit, as a sheet. And then we have spontaneous action potentials via special cells, which are called pacemaker cells. And we're going to talk about pacemaker cells and how they work when we get into the cardiovascular system. And we'll talk a little bit more about it too when we get to the digestive system. So what that means is they can generate their own action potential. So when we say spontaneous, it does not need the nervous system to provide that action potential. It doesn't need some outside stimulus. It just happens all on its own. So you get contraction, relaxation, contraction, relaxation. And wouldn't that be really important in our GI tract and in the ureters, right? Because we want constant movement of our food through our GI tract. We want constant movement of urine from our kidneys to our bladder. So that's single unit smooth muscle. And it contracts all on its own without a stimulus. So no stimulus required. It's just constantly doing its thing. It's like those rowing teams, the crew teams, you know, where if one person says row, row, right? And all the people row. So that's what these cells do. You have pacemaker cells that start the action potential. Ions flow through gap junctions, and you have rhythmic contraction. That way we have constant movement through the, again, so the GI tract is an example of this. And the urinary tract is a good example of this. All right, so that is a summary of the major differences between skeletal and smooth muscle.